So once again, I'd like to thank the Atkinson Center and Biological Environmental Engineering Department for helping sponsor this seminar series. And so today, I'm really happy to welcome Corinne to the seminar. She's at the Royal Society Research Professor of Climate Change at the University of East Anglia. She got her bachelor's at University of Montreal, master's in atmospheric science and ocean science from McGill, and a PhD in oceanography in Paris. So research is on the interactions between climate and the carbon cycle and looking at how climate change and variability affect land and ocean sinks of carbon, and also the drivers of CO2 emissions. Corinne initiated and directed the annual publication of the Global Carbon Budget for over a decade, and this gives a detailed information concerning the sources and sinks of carbon to the atmosphere. Also, the sinks of carbon to the land and ocean. She's author on 3 IPCC reports, and she chairs the Francis High Council on Climate, so a member of the UK Climate Change Committee, and they're independent councils that provide evidence-based advice to inform government's response to climate change. So welcome, Corinne, and thank you for your patience for us getting us set up. And I think we're ready for you. So
thank you very much, Peter. Thanks everyone for having me today. Can you give me a thumbs up if everything's okay? Yeah, excellent. Okay, it's my great pleasure to be with you today. I'm speaking from Paris, actually, where it's quite late today, but I'm really pleased that we can do this exchange. I'm going to talk about the global carbon cycle and try to give a flavor of where we are with our understanding of carbon emissions and their partitioning in the environment, particularly focusing on the last decade and then the last couple of years, and with a little bit of a perspective of where we're going post-COVID. As a background, I want to show you this figure, which is really a condensed version of the relationship between emissions of carbon dioxide, which is the anthropogenic greenhouse gas that is most responsible for climate change today, and temperature. Now, we know very well from understanding of the physical science, from observations of past climate, that greenhouse gases cause the warming of the climate system, the century warming that we have seen, which is shown here in this figure. And because of our combined understanding, we're also able to say that as long as the emissions of carbon dioxide, the bottom curve here, which are the global emissions that have grown over the last century and a half, as long as they are not returned back to actually zero, then the temperature of the climate system will continue to rise. So it's not enough to stabilize the emissions. You have to actually stop emitting carbon dioxide to the atmosphere, because CO2 is a long-lived greenhouse gas. Once you've emitted it stays in the atmosphere for a long time. Now, the fastest, the quickest you bring these emissions down to zero, the lower the temperature warming. If you're able to keep your emissions below zero for a little bit, like is the case here, the zero line, you see it, a pale gray line over here, then your temperature can go down a little bit, but by and large, you'll stabilize your warming at that point. We've had so far about 1.2 degrees Celsius of warming, and this is actually an enormous amount of warming in planetary term. You have to compare this perhaps to a fever, a body fever of 1.2 degree, you would be really ill, you would feel uncomfortable. And the more the warming goes up, the more uncomfortable you get. And it's the same with the planet because the environment is in balance with the water cycle and the biosphere. With 1.2 degrees Celsius warming today, we're seeing a lot of impacts, a lot of heat-related impacts, heat waves, extreme temperatures, wildfire outbreaks. We're seeing also a lot of impacts in the water cycle, particularly extreme rainfall. But the higher you get in temperature, the more these impacts become stronger, extreme, they last longer, and the more the types of impacts start expanding in the climate system, from impacts to corals is probably the most vulnerable ecosystem, then the polar impacts, melting of the snow and ice, then impacts on biodiversity, then impacts on water resources affecting water availability, then economic impacts all the way to potential tipping points in the climate system. So these are very, very serious changes, and that's why it's a good idea to limit warming as low as possible. Now, if I move to the bottom side here, which is what I'm going to talk about, is the carbon cycle. The current policies that are in place are not enough to limit warming well below 2 degrees, which is what has been agreed internationally as part of the Paris Accord. They're not enough to limit warming at that level. They would lead to possibly 2.7 degrees Celsius, according to the latest estimation with current policies. We know from the carbon cycle research that the more warming there is in the climate system, the more risk there is to destabilizing stocks of carbons that are stored in the terrestrial and biospheric environment. And we have proxy for this from paleoclimate. We have two types of proxies that are particularly revealing. One is a very, very old reconstruction, the one in yellow here, reconstruction of changes in atmospheric CO2 a long, long time ago, 55 to 57 million years ago, where there is a pulse that is registered in the carbon isotope, which suggests that large quantities of carbons were released probably from either permafrost or methane hydrates or both. Now, the conditions today are very different. The continents are in different position, and this is not a proxy for the future, but it does show that there are real tipping points, real threshold in the climate system that could be triggered by warming that would exceed 2 degrees in particular. And the other proxy that we have is ice core data. So this is the record of about 1 million years ago of atmospheric CO2 of air trapped in in ice core that scientists went and recovered from Antarctica and other places. And if you measure that very old ancient air, you see also variations of atmospheric CO2 that are indicative that the natural environment responds to, in this case, changes in climate that were triggered by changes in the orbital forcing. It's not the case today. Today, the case is very clear that it's the emissions of carbon dioxide from human activity that are causing the warming of the climate system. But it's also equally clear, as I will go into in a minute, that the terrestrial reservoir and ocean reservoir of carbon are not staying still in that big change. Last point on that background slide is that in order to reach net zero, which is needed to tackle climate change, with our understanding today, it's not possible to reach net zero, to reach absolute zero, I should say, in all of our activities where we use CO2 emissions, particularly agriculture, emissions from agriculture and emissions from aviation. You can't bring them absolutely to zero. And so in order to reach net zero, which is no net emissions of CO2, you have to offset some of your emissions. And this comes with a whole lot of additional challenges, which are detailed in this report here and in many other places. I won't be covering this today, but I will be covering the contemporary global carbon cycle. My presentation has 5 parts. So the contemporary global carbon cycle is really how the pools that are sort of responsive on timescales of years to a decade, maybe up to a century, what is happening to them. And there's a lot of carbon stored in these pools. So we're talking here about vegetation, we're talking about permafrost, we're talking about soils over on that side. There's a bit of fluxes in rivers and coasts. There's also a bit of fluxes in sediment, and there's a very, very big pool of carbon that is stored in the ocean itself. There's natural exchanges between these pools. The 2 main pools that I'll be talking about is the ocean on one side and the terrestrial vegetation on the other side. Big fluxes, natural fluxes between these pools and the atmosphere on the natural environment. And in the natural environment, you see, so this is billion tons of CO2. I'll be using this unit a lot today. So it's 10 to the 15 grams of carbon. It's simply a mass of CO2 here. So the amount of CO2 in the atmosphere pre-industrial was equivalent to that number here. You see 2,200 billion tons of CO2, equivalent to 278 parts per million, if you've heard that number before. The ocean stores 50 times more carbon pre-industrially than the atmosphere. So it's a vast amount of CO2 stored in the ocean, carbon stored in the ocean, and the terrestrial biosphere stored about 7-8 times. So that includes soils and everything. Now, the perturbation, the human perturbation of the carbon cycle is here on the left-hand side. We've tapped into, well, what remains of the fossil fuel reserves, which are the economically viable reserves. Now, resources are a lot bigger, and they might become economically viable with more technology here. But the amount that we are tapping in these resources is really very large. So the fluxes of fossil emissions, so this is mostly burning fossil fuel, for example, for power station, for petrol in your car, for heating, if you heat with a gas boiler, for industry. So these are all behind that. 35 billion tons of CO2 every year, and then land use change. So that's mostly deforestation, but there's also other management processes here, which is a flux that is a lot smaller, but still significant, especially historically. So these emissions, what they are doing is putting CO2 in the atmosphere. CO2 stays on average 100 years in the atmosphere. There's a long tail, so some of that CO2 will stay a few thousand years. But a lot of that CO2, in fact, more than half of those emissions each year do not remain in the atmosphere. In fact, this is the part that remains in the atmosphere, 19 here, 19 billion tons of CO2, but the rest is absorbed every year by the terrestrial biosphere and by the ocean, which act as sinks for carbon on a year-to-year basis. So if these natural sinks did not exist, then more than all of that CO2 would remain in the atmosphere, and the rate of climate change would be a lot faster. What I've put here at the top here, this little line that you see, very thin line, is the concentration of CO2 in the atmosphere. So we put every year, we continue to add CO2 in the atmosphere. So if you measure the stock, so how much CO2 molecules you have in the atmosphere, then it's growing extremely rapidly. If you've heard of the Mauna Loa Hawaii Observatory and Dave Keeling, so this is what he started to measure in 1958. When I look at these 5 components, so the 5 components that I just explained, but there are changes through time, which is what you see here. Since 1958, you see this evolution. So at the top here, you see the two sorts of emissions. So I said fossil fuel, 35 petagrams, billion tons of CO2, and land use, 4 billion tons of CO2. Historically, land use was the biggest emitter of CO2 until about the 1950s, 1960s, where fossil emissions really kicked off, initially coal very much, then oil and gas. And you see today that these emissions are really growing extremely rapidly. The evolution of CO2, because it's causing climate change, is closely monitored, but actually the emissions are reported, the emissions themselves come from reporting from governments, but they are by and large very reliable, because emissions come from energy, and energy is taxed. So it's a source of revenue for governments, and therefore the reports are closely scrutinized. At the bottom, on the bottom side of this graph here, you see the mirror of these emissions, which is where do the emissions go in the environment? I mentioned already the atmosphere, the terrestrial biosphere, so the land and the ocean, and you see here their evolution through time. The atmosphere change is measured. The ocean is both measured thanks to oceanographers who go around the ocean, and also automated instruments now to do measurements in situ. So the ocean is measured and is modeled. I do ocean modeling, so this is my bread and butter here, so to speak. And the terrestrial biosphere is mostly modeled through a representation of ecosystem, computer representation of ecosystems that are based on processes. These 5 terms there are estimated through methodology that is almost completely independent from one another. So the fact that the red line here is the exact mirror of the top emissions, the fact that we can account for all of the emissions of carbon dioxide with our independent estimates of ocean, land, and atmosphere suggests that we have a very good understanding, or a reasonably good, I don't want to overdo it either, but a reasonably good understanding of the dynamics of the carbon cycle. And this is true both for explaining the size of the carbon sinks today, but also explaining their dynamics, which you see they've been growing through time. So this was the way to present this slide in a positive way. But if you start looking at the differences now between this red line and the sum of the ocean, land, and atmosphere, you see that there are pretty substantial differences, and the differences have a signal that looks like climate variability, but is not attributable to any one single mode of climate variability. So probably a combination of errors in data, errors in uncertainty, errors in model representation of the carbon sink. And this, we call this the carbon budget imbalance. And this is really shows the cutting edge limit of our understanding in carbon cycle. In fact, all the eyes of the carbon research community are focused on this, trying to understand where this gap comes from. So the distribution of these emissions, which are at the top, fossil fuel, land use, and then the sinks, ocean and land, is very different. So countries have different drivers for emissions. Regions have different land and ocean fluxes because they're modulated by the regional climate, the temperature, the winds for the ocean, the rainfall pattern for the terrestrial ecosystem. And so that has implications for the way that the different countries and different regions have responsibility for both tackling their emissions, but also for taking care of the stewardship of their carbon reservoirs and carbon sinks. I move to the second part of my talk. My talk has 5 science sections. I'm going to talk about the latest trend in the fossil part, so the biggest emitter of CO2, the latest trend in CO2 emissions. I'm now going to first comment on the pre-COVID emissions. So what you see here is a time series, so evolution with time of the emissions of CO2 at the global level. And it starts in 1990, and we had a period of extremely rapid growth in CO2 emissions, 3% per year over a decade, 2000 to 2009. This was sort of broken down by the global financial crisis in 2008, 2009. And following this, there was a slowdown of these global emissions, so that the last decade before the COVID crisis, the growth was 3 times slower than the decade before. This change, interestingly, has been attributed to the presence and the presence of climate policy worldwide. There are today more than 2,000 climate policy worldwide. At least every country has at least one climate policy. A country like the UK, France, and has about 100 climate policy. I mean, I include the energy policy there. And the US has probably over than 200 policies by now. We've done, with my colleagues at the Global Carbon Project, we've done a study published a few years ago, 3 years ago, looking at the countries where the emissions are decreasing. So at the time, there were 18 countries where the emissions were decreasing for at least 1 decade. They were decreasing based on territorial emissions, but also including imports, they were decreasing. Today, this number is 24. So this group has been joined by Japan, by Mexico, by also other European countries. The US is part of this. The US is over here, this little post stamp over here. And what we did in this publication is we looked at what were the physical drivers of this decrease in emission, and very importantly, do these countries what do they have in common? So is there like a key to success? What is the central, what is the commonality between these countries? And we found 3 things. The first is that these were the countries where there was a decreasing use of energy. So not ever growing use, but decreasing use of energy, mostly because of energy efficiency. There, the global financial crisis played a role also a little bit in that period. The second was, these were countries where renewable energy was replacing fossil energy. Now, this is really important because the countries that did not make it to that group very often had renewable energy growing alongside fossil energy. So to reduce your emissions, you have to take out fossil energy. It's not enough to just deploy renewable energy. And these 18 countries had that in common. And the last point, which is the most interesting, is that the more the policies in place, the more the emissions decrease. And really a very nice indication, one of the very few papers that showed a linkage, although we couldn't quite go all the way to cause and effect, but at least a relationship between the number of policies in place and the size of the emissions dropped. So now post-COVID, so we had COVID. I will go into a lot of detail in a minute in what happened during the COVID crisis to CO2 emissions, but I do want to give the numbers straight away, which is that during the COVID crisis itself, 2020, when we had the biggest lockdown, the emissions dropped by 5.4%, in 2020, and they have rebounded already in 2021. Now, this is normal that the emissions would rebound because we did not tackle climate change, we tackled a crisis, a pandemic. And the way that we did this is by stopping the activities that we did, putting very big constraints on people, particularly on mobility. And so we didn't actually invest in infrastructure, green infrastructure. We just stopped using what we had. We didn't change our car for an electric car. We just did not use the car. The car is still there. So as soon as the constraints went, then the emissions are coming back up again. But the trajectory of post-COVID is really unclear at this stage because there has been some investment in green infrastructure during COVID, not nearly as much as is needed. Still, there has been some, and prices are coming down, and it will take a little bit of time for these investments to pay off. If we go into one level of detail more, now I show you country by country, what happened and the projection, what happened during the COVID crisis. So you see the United States here that had a drop of 11%, I think, during the COVID, and then a rebound of 6.3% over here. Mostly in the countries where we do have already data and projections for 2021, mostly the emissions came back on the trajectory where they were pre-COVID. So you see the United States, the emissions of CO2 were coming down, and the 2021 rebound is below 2019 levels of emissions. Same in Europe. In India, the emissions were going up, and then the rebound is above 2019 level, and same in China. Whereas all the other countries together, the rebound is not nearly as close, but we don't have specific data yet. So that's why I say that we don't really know what the next year or two will look like. I want to dive into near real-time detection of CO2 emissions. What I've showed you so far is really the conventional reporting of emissions. So this is essentially the way that the reporting infrastructure, I guess, for the lack of a better word, is organized. As countries report their energy consumption every year, this gets converted to CO2 emissions based on conversion, known conversion factors, and this happens once a year. Now, as you know, we had the COVID crisis. Unless you were sleeping somehow, you might actually even remember how it felt for you at the very, very beginning of this crisis. And for me, I had quite an experience on that day here, 27th of February, because I had a journalist ring me from the Associated Press in the United States. And he said, look, we have all these confinement measures that are starting to be in place. At that time was most of China, Italy, it was starting in the US. You see the pale blue there on that map, and no measures widespread. And the question to me was, is that going to have an impact on CO2 emissions? And I'm an expert in CO2 emissions, and this is really it was really an obvious and very, very obvious question. It was actually a question that I would have liked to have the answer myself, but I felt so embarrassed that I had no idea. I had absolutely no idea. So I sent the journalist away, gave him a few names, try this person, try that person. And then, of course, it got worse and worse. And it got to the point very, very quickly where I had journalists on my back every day with that very same question. And wasn't it puzzling that we're in the middle of this big pandemic and so many people were interested in the environment, I haven't quite understood what happened there, but there was really a mental connection between the pandemic and the environment at that time. And so I got into a bit of an obsession myself, and I thought, I need to know what the emissions are doing at that time. So I did what you do in those times is I called my friends and long-term collaborators at the Global Common Project, and we had a phone conference, we exchanged views. Nobody had any idea what was happening to these CO2 emissions because we had no data. And so, but we all agreed that actually we need to try something, we need to figure out how to get to that estimate. So I spend the next few days frantically looking at the internet for data. And then something happened that was really very special, is that data that did not exist before started to appear. So lots of mobility trends started to appear, air traffic data, highway statistics, bridge statistics, TomTom data, Google Analytics put all their data on the web, smart meter data started appearing, some companies put their data on the web. There was lots of very, very chaotic but interesting different sources of observation on the web. So we, with my colleagues, thought, okay, that's what we have, let's use it. And so we split the emissions of CO2 among their emitting sectors. So CO2 globally comes from power, so generation of power, electricity mainly, industry, then surface transport, so that's cars and trucks and vans, buildings, so residential and public, there are two types of building, and aviation. And so the percentage that you see over there is how much these sectors produce in terms of emissions. And we use I think the 430 time series that we found, and we looked at the data. Each of the point that you see here is a time series data, for which we have extracted the days where these countries, the countries where the time series originate from, were in lockdown. When the countries were in full lockdown, by and large, the emissions from the power sector decreased by about 15%. The emission from the industry, very few data there, about 30%. The emissions from surface transport, heaps of data, were cut about in half. Residential building increased a little bit, 5%. And then aviation was the sector that was the most touched, 75% cut in aviation emissions when countries were under lockdown, but this is only 3% of the global emissions. So what we did is we had this data, we made this analysis, and then we looked for the 67 most polluting countries. When did they start to be in different levels of confinement, with the full lockdown being the level 3, but also we defined different levels for which we had data, and we could characterize sort of a transition between sort of like a normal functioning economy and full lockdown. And based on this, we did a massive back of the envelope calculation, very simple calculation. And we could, in fact, establish that the emissions from each of these different sectors, how much were they cut during full lockdown. With the surface transport here, you see being the sector that contributed most to the decrease in emissions, even though the aviation was the one that was struck the hardest. And based on this, we managed within 25 days of having this conference, this first conference call, to submit a paper that eventually was published a month later in Nature Climate Change. And this paper said that during the one day where first week of April 7, as far as we can establish, 2020, the global emissions of carbon dioxide were cut by 17%. So you do all this confinement, and the decrease in emissions was cut actually not as much as you would think, although the countries that were, when you are in the countries that were under full lockdown, the emissions were cut about by a third. So it means that a lot of our economy, or our emissions, I should say, not our economy, a lot of our emissions actually are operating in the background without not that much economic activity associated with this. Because our own analysis was based on confinement measures, we were only able to do it for the first year. We came up with a projection of decrease in emissions between 4 and 7% for this first year. It ended up to be 5.4, so admittedly a large range, but the projection was made very early. But others have picked up a similar methodology that goes further, that actually is based on more quantitative emissions and not just emission change as us. And the latest that they're able to show in this paper that is coming out in ERL very soon is that if you look at the sector level here, this is 2 years, January 2020 until January just now, 2022. You see that the emissions from ground transport in green here are still, in fact, quite a bit below 2019 level, and same with aviation, both international, mostly international, less so domestic, and that the emissions from the power and industry sector are then above or very close to 2019 level. So all this to say that actually the COVID crisis stimulated, in fact, new ways to capture the evolution of the emissions, and these ways are now here to stay in the scientific world. There is maybe, no, I'll skip this. I'll just go. I want to touch on two different sort of rapid assessment of CO2 emissions. One can be done with satellite data. You may know that column CO2 is measured from satellite observations. Beautiful, beautiful pictures are coming out of the NASA OCO2 observatory. It takes a long time to develop products with satellite data, but once they get operational, they're really incredibly informative. And at the moment, the information, the CO2 fluxes, so what the satellite measures is the total CO2 that is in the air column. And so you have to go from there, that information about this massive CO2, to the information about the fluxes between the surface and the atmosphere. So you need to have methods that inverse, what we call inverse this information. And they're at the moment at least as good as surface-based inversion, but they provide a lot more information, and they're more consistent with our understanding of the fluxes in the terrestrial biosphere in some places. But the disadvantage of the satellite-based estimates is that they see, sorry, they merge together both the anthropogenic emissions, but also the natural fluxes. So if you have the fluxes over America, for example, you don't know, at least not directly with this information, you don't know if the emissions are from the power industry or if they're from natural forest. So you need to do more work there to do that. But lots of things are upcoming there. And I want to talk also about an alternative method to estimate CO2 emissions. And this one is based on oxygen data. Now, oxygen, there's a lot of oxygen in the atmosphere. Oxygen is taken up by the biosphere for photosynthesis, but it is burned. So when you burn fossil fuel, then there's a combustion process and it consumes oxygen. So we know the ratios of this. And so you can combine. So this is measurements in the atmosphere at one station, Weybourne Station, not far from where I live in the United Kingdom, hourly measurements of CO2, of oxygen. And when you combine them with this ratio, oxygen plus 1.1 CO2, effectively you remove the effect of the biosphere, because photosynthesis always takes the same amount of CO2 for the oxygen that it consumes. So that the APO here, atmospheric potential oxygen, is really a signature of fossil fuel emissions. But when you detrend it over here at the bottom, the signal that you see is dominated by weather. Because the air around us originates from, I mean, if it's from the left here, it's from the city. If it's from the right, it's from the sea. So just the wind direction creates a very, very big signal. But you can remove this signal with machine learning by including the weather information that you do have in this data, and therefore extracting a clean signal. And we've tested this methodology in a publication that is in press now, and we're able to show in red here, you see the change in CO2 emission during 2020, so the COVID year, compared to 9 background year. And if you integrate it, you see at the bottom the signal a lot more clearly. But with this one station in England, you're able to detect the change in COVID due to the confinement by applying this data and removing the weather methods. So we think that with a little bit more refinement, we would be able to start detecting and verifying changes in CO2 emissions from direct observations. Okay, part 4, 2 parts left in my presentation. Part 4 is very short, is about the land use change emission. So those of you who have very sharp eyes might have noticed the top here, which is that the total emissions from land use change and from fossil emission has been relatively stable in the past decade. That's because the latest estimate that we have about land use change emissions, these emissions have been decreasing a little bit. Now, I want to stress that the uncertainty is massive behind this. So I have actually, I don't want to say no confidence, but very little confidence that this is correct. So let me dig into this just a little bit. The emissions from land use, they're from primarily deforestation, but also from abandonment of agriculture. The United States is a good example for this, where a lot of land gets reconverted after agriculture is no longer viable. Same in Russia and Europe and Canada, a lot of this is happening. Another source of emissions is wood harvest and other management processes. That's all the sum of this is what has caused this sort of gentle decrease in emissions. But the land use, the total net land use emissions, is really made of 2 processes. It's made of a bunch of processes, of land use processes that emit CO2, like deforestation and like wood harvest, which is what you see here. And there's a bunch of processes which take up CO2, which is what happens after the abandonment of agriculture or when forestry regrow the trees. And these processes are at the bottom. And as far as we can tell, although the data is not very reliable, frustratingly, the emissions, the gross emissions from land use change have been relatively stable in the last decade or so, whereas the sink have actually increased, so that the sum of these 2 is what leads to a small decline in emissions. Now, on the one hand, you could say, when you look at it this way, you have 2 leverage for using land to tackle climate change. You can stop the deforestation and you will gain all this in terms of emissions, and you can enhance your regrowth and you can push the sink, the gross sink, down a lot more, which is true to some extent, because in the management processes like wood harvest, for example, these 2 fluxes are related. If you don't have wood harvest, you don't have regrowth of wood after wood harvest. last part. So I'm moving now to the land and ocean carbon sinks. So a little bit on the physical understanding of these sinks first. So the terrestrial sink here, I'm talking about the sink in natural forest, natural environment, is really a response to rising CO2. So plants need CO2 to grow for photosynthesis. To get that CO2, they have little stomata, so they're little pores at the surface of their leaves. And if they open these pores for letting the CO2 in, and if the concentration of CO2 in the air is very high, they don't need to open the pores so much, the stomata so much, and they are more efficient at using water. So that's like, in a nutshell, that's the process. And so this has led to an enhancement of the terrestrial vegetation, which is more, in fact, than the land use change emission that I showed you before. So the overall biomass is getting bigger, but in some places of the world, we're clearing it, cutting it, and in other places, it sort of pops up. So actually, the vegetation looks really quite different than pre-industrially. So that's for the terrestrial sink. For the ocean sink, is really, so it's a physical chemical process. So you have the CO2 rises in the atmosphere. It increases the partial pressure of CO2 because you have these molecules moving. The CO2 dissolves in the water, but it doesn't stay in its CO2 form. It combines with water and forms bicarbonate. It's a bit of a shortcut, but that's the equilibrium. In the process, it acidifies the ocean, big worry. But this process really means that most of the carbon in the ocean is in the bicarbonate form, where it does not exchange with the atmosphere, only CO2 exchanges with the atmosphere. And that's the reason why the ocean contains 50 times more CO2 than the atmosphere. Anyway, both of these things take up 25 to 30% of the emissions each year on average, but they respond to climate change and variability. I'm almost done now. Just 3 slides to finish. The ocean sink, so these are different estimates. I won't go into detail here, but different estimates of how the ocean sink has evolved through time. It's growing, it's clearly growing with rising CO2. Unclear when CO2 decreases, how much faster it will grow or not. There are large uncertainty. You see the last decade, particularly large uncertainty that comes from the evolution of the Southern Ocean, because winds have picked up in the Southern Ocean, and Southern Ocean is extremely windy and extremely active as a carbon sink. There's also a big known unknown in the in the ocean, where the ocean acidification in particular is affecting marine ecosystem in a way that is not known and could influence the uptake of carbon in the ocean. On land, the land sink has grown over the past decade, but it has a huge year-to-year variability. This is a response to climate variability, and you can see very well with this figure that the land sink is very sensitive to climate variability and therefore to climate change. Last slide here. Through the annual update of the global carbon budget for this year, for the first time, the team has separated the sink's response to the increasing CO2 versus the sink's response to the climate. So these two things are combined now, and the sinks continue to rise. But behind that, there is an attribution process. There are 2 processes, and clearly here the response to CO2, to increasing CO2 is that both sinks continue to grow in response to rising CO2, but the response to climate is quite different, with the land sink in particular having these hotspots of decreasing sink, putting their CO2 back into the atmosphere, and the ocean warming, causing a very gentle but widespread weakening of the carbon sink. And exactly how these things will evolve is not 100% clear at the moment, but what is actually completely clear is that the response to CO2 itself will weaken through time. We understand the processes there, while the climate response will grow. On this, I will stop here and give the opportunity for an exchange with discussion. Thank you very much.
So we could take questions from here. Also on the webinar, if you could type your questions in on Q&A. Corinne will can respond there. So question from here. First. Do we have one? Go ahead, please. Yes, please.
Okay, so compared to like during COVID, is there any significant changes in the ocean and land carbon sinks? Anything significant or just not?
So the question is, are there any significant changes during COVID in the ocean and land sinks of carbon?
I'm sorry, Peter, I haven't understood the question.
So the question is, during COVID, could you detect any changes in the land sink or the ocean sink? Anything
Yeah,
significant?
good question. There were significant changes in the land and ocean sink, but not as far as we know, changes that were attributed to COVID itself. So there were natural changes, particularly natural variability in the Indian Ocean, but not for the carbon sinks themselves. We haven't been able to look at land use change emissions in this analysis. I don't expect how much that big a change, because at least the management part is needed, the part that is related to agriculture, but we couldn't go very deep in that respect.
Do you want to take a question from the webinar?
Yes, absolutely. So the first question is, to what extent quantitatively can aggressive worldwide tree planting and reforestation offset fossil fuel emissions and reduce atmospheric CO2? So you can do some artificial carbon sink by, I mean, I call this artificial, although it's quite natural, but it's still managed. Carbon sink by reforesting the world, but it's nowhere near the size of the fossil fuel emissions today. So you wouldn't do this to offset the emissions that you can cut down to zero, because it's a lot easier, in fact, or at least it's more direct to reduce the fossil emissions, but planting tree will have a big effect. So if you look at the numbers that I showed earlier, so the fossil emissions, 35 billion tons of CO2, deforestation, gross deforestation between 10 and 15 billion tons of CO2. So you could say if you stop that completely, you have a leverage of about 10, 15 billion tons of CO2, which is big, but you still have this monster fossil fuel emissions on the other side. Another way to think about this is to think, if we were to reforest all of the forests that we have cut so far, if we were to re-put back the vegetation the way it was, you would have about 70 parts per million CO2 lower, and we're already 120 parts per million above pre-industrial CO2. So it's big, and it will help to plant trees, and we need to actually get on with it and do it well. But you can't do this instead of cutting the emissions that we know how to cut. You have to do it for the emissions that we don't know how to cut.
Thank you. Do you have another question from here? We have one from here. Go ahead, please.
Sure. So regarding satellite estimations, what methods are being developed to try and separate the emissions from natural flux and emission data?
So the question was regarding satellite, how to separate natural fluxes of carbon from the emission data.
Yeah, thanks for your question. So mostly you look at the regional distribution. So you can, I mean, the fossil emissions have a fingerprint that is very specific. It's associated with power plants, it's associated with cities, whereas terrestrial biosphere, where it's most confounded, is associated with forest. And there's also a day-night cycle. So you can use all this information to constrain your model. You do a prior estimate. So you start with a best guess of what your fossil emissions are, and then you use an optimization process to sort of disentangle those two. So this is, to my knowledge, the main method to separate them. There's also methods that are combining different sources of observations, including CO2, but also other pollutant, but I'm a little bit less familiar with those.
One more from here. Yeah, please.
Yeah, so you mentioned that countries with declining emissions tend to have renewables replace fossil fuels. Is there a possible way for countries that are trying to industrialize and put an emphasis on renewables to cut emissions?
So the question was that that you mentioned that in countries where emissions are declining, that renewables are replacing fossil fuels. How about in countries that are industrializing? How can they go about cutting their emissions? Is that right? Yeah.
So, so yeah, you mean emerging economies? How can they go about? Yeah. Thank you for that question. I mean, this is really the political economy. So in industrializing economy, take India as an example, where there's a very big demand for energy. Really, it's a question of I want to say controlling, but planning, sorry, of planning the growth in energy so that you can develop your trajectory of energy as much as possible based on renewable energy. So there are places where you can do this more easily than others. For example, where there's no fossil fuel resources handy, it's a lot easier. Where you already have a fossil fuel industry, like South Africa, for example, where they have a lot of coal industry, it's a lot more difficult because you have your industry is established, it creates job, you know how to do it. And the tendency, all the inertia will be to finance this industry that already exists. So you have to really be sharp and alert and plan well so that you channel all as much as possible of your funding, your effort, but also beyond that, your city and your national planning towards renewable energy. And the way that this is done at present is through the subsidies for renewable energy, some of the money that go from rich to developing country, the realization that in many cases it's cheaper to develop renewable energy. The World Bank has stopped to finance some of the coal power plant because it's not the cheapest alternative, which they're bound to, which they have to fund. So essentially, that's like that. I should say, though, that there were a lot of rich countries where renewable energy are being deployed alongside fossil energy. For example, Canada and Australia were among those, at least in the period that we studied. And there is really about climate policy and putting a price on carbon. And actually a price on carbon internationally is also very important, so that the polluting effect of emissions is costed properly.
Thank you. Do you want to take a few questions from the webinar?
So one question is, what is the difference between carbon sinks and reservoirs other than the way they are measured? The reservoir is really the stock of carbon, and the sink is the flux, how much it absorbs every year. So one is a number of molecules of CO2, and the sink is how many more CO2 goes every year. So when I say the ocean sink is growing, do I mean its capacity to intake CO2 is greater, or it continues to take CO2? So I mean it continues to take CO2. In fact, the capacity or the efficiency of the ocean decreases with every molecule. The more CO2 you put in the ocean, the less it takes in terms of the percent of the emissions. And that is because I mentioned that when CO2 dissolves in seawater, it goes eventually to bicarbonate. But this direction, this process needs carbonate, and carbonate goes down the more CO2 you have in the ocean. So there's a resistance, so to speak. There's a question about methodology. What kind of methodology was used to say that the decrease of greenhouse gas was attributable to methodology, to policy implementation? Okay, so two answers to this. In the study that I led, we were not able to attribute it. We were just able to say the countries that have more policies, now we counted them 1, 2, 3, 4, as a proxy for policy sort of uptake, was correlated with the number, the size of the emissions decrease. So that's we could not go any further than this. However, since we published our analysis, a different publication was made by colleagues at the London School of Economics, and they included a model. So they had a model of dynamics of emissions, and they included the impact of policies there, and they were able to quantify the impact of the. Well, at the time they published 1,800 policies worldwide on emissions, and they were able to show quantitatively that the change in the slope of emissions from 3% per year to 1% per year was caused by these almost 2,000 policies worldwide. It's just super interesting and revealing, actually. And it says that, I mean, it does mean that climate policy actually work, but they're not at the right scale at the moment.
Another question, yes, one more question, I think. Go ahead, please.
I have a question about, so with growing population, like the need for increased agriculture. I was wondering what your thoughts were on how to achieve that. Deforestation is such an important part in achieving higher agricultural lands. I was wondering what your thoughts were on how to reach almost a solution to that.
So the question is, with growing population, increase in agriculture, increased land use, how do you solve that conundrum? Is that right? Did I get that? How do you balance those two things and decrease carbon emissions?
Yeah, I mean, very good question, very good point. I mean, land use change emissions are not the main source of emissions. So for now, we have a lot to do with just fossil fuel emissions. But in terms of beginning to manage land, creating value out of existing forest and manage forest is one way to do this. I mean, one of the reasons why the deforestation is so big is because at the moment, a lot of the economy relies on agriculture. A lot of the agriculture is not actually the best use for food. For example, we eat way too much meat, we eat way too much protein, period, meat or anything else. Just reducing the red meat dairy intake would reduce the pressure enormously on land in a country like the UK, release land so that you can reforest and use the land for other things such as planting trees, for example. Oh, there are lots of questions I hadn't seen. Well, I won't be able to answer everything. Thank you so much.
So, yeah, thank you. Let's thank Corinne again.
Thank you very much.
It's quite late in Paris, so we should let her go. So thank you so much for coming and talking to us. Very interesting.
Thank you. Have a good day.